Hey guys, in this video, we're going to talk about how to solve linear first-order differential equation. Linear first-order DE has the form dy over dx plus ypx equals qx, where dy dx is just the derivative of the function y with respect to x, p of x, q of x, they're both functions of x. Notice that this can also be written as y prime plus ypx equals q of x. And then our main idea of solving it is to make use of the product rule of derivatives, which is yz prime equal to y prime z plus yz prime. So we're wanting to find such a function of x, this function z, to multiply on both sides of the equation. So it gets distributed into each of the terms, and then our equation is going to become y prime z plus y px z equals qx z. We're hoping that our left-hand side expression here will look exactly the same as the expression here, so that it can be transformed into the product, the derivative of this product yz. So if we compare the first term in our left-hand side with the first term here, we see that they have already matched. So what we are hoping here is the second term also matches this second term. So we want them match. To summarize, our idea here is to find such a function z of x such that these two guys will look the same. What does it mean by they look the same? It means that we will have to have px times z equals exactly z prime. So px times z equals exactly z prime. And therefore, our left-hand side will equal to that, which can be transformed into this derivative of the product, right? And that's going to be equal to our original right-hand side, which is qx z. And after that, we will take the antiderivative on both sides of the equation with respect to x, so that the antiderivative is going to cancel with this derivative thing to make that prime disappear. Then we're going to have yz equal to antiderivative of that with respect to x. Then we can divide both sides by z to solve for y explicitly. Divided by z, so that this equation is solved. Okay. Next, we will talk about how to find such a function z, so we can have p of x times z equal to z prime. We're going to take a look at a few different simple situations and then solve them, and from there we will figure out a pattern, so we will know how to find such a function in a general situation. Situation number 1. When a function p of x is equal to 1. In this case, the equation is going to become z equal to z prime, which means that the derivative equals to the function itself. And if we search our inventory of the derivative formulas, that we see that the only function that satisfies this condition will be the exponential function e raised to the power x. So we're going to have z equal to e raised to the power x. We can sort of do a quick check here. Check to see that the derivative of e to the x is e to the x. And then situation number 2. When p of x is a polynomial function, let's say 2x, then we're going to have 2x times z equal to z prime. So what we are seeing here is after we take the derivative of this function, z, this function is going to stay the same here, and then it multiply with something extra. And that something extra must come out from the derivative of the inside function in the chain rule. So we will expect the function z look similar to e raised to some power, where that power should give you the derivative 2x. So we're gonna try this function e raised to the power x squared, because the derivative of x squared is gonna be 2x. And then we sort of also do a quick check here. Check to see that the derivative of this is going to be this one itself multiplied with the derivative of the inside function, 2x. So it looks exactly the same as this equation. It does satisfy it. And at last, we'll take a look at situation number 3, where p of x is equal to cosine of x. In this case, the equation will become cosine x multiplied with z equal to z prime. And then we should expect something similar happening, which is that the z function is going to be e raised to some power, and that power should be the antiderivative of cos of x, which is going to be sine of x. So our z of x is going to be e raised to sine of x. Do a quick check here. The derivative of e raised to sine of x is going to be this function itself multiplied with the derivative of the inside, which is cosine x. So it does satisfy this equation. After we check these 3 simple situations, we have gotten a clue, which is that the z function will always look the same as e raised to some sort of power. And that kind of power is always going to be the antiderivative of p of x. Because in situation number 1, when p of x is equal to 1, you have your power being x, which is antiderivative of 1. In situation number 2, when this is 2x, the power is its antiderivative, x squared. Situation number 3, when this is cos of x, the power is sine of x, which is also its antiderivative. So in a general case, we should have function z being e raised to the power, which is the antiderivative of p of x. For such a z function here in general, we're going to give it a name and call it integrating factor. We have demonstrated the procedure of solving such a type of differential equation and also know how to find the integrating factor. Now let's take a look at an example to see how to do it. This example, we have x multiplied with the derivative which is dy over dx, minus 2y equal to x squared. So the first thing we do is to write it in a way that we are familiar with. So we want to write x times y prime minus 2y equal to x squared. Compared to our form that we discussed before, which is y prime plus ypx equals qx. Something that is different here is we have an extra x multiplying with the y prime. So we need to get rid of that. And to do so, we can just simply divide both sides by x. Okay, then we're going to have y prime minus 2 divided by x multiplied by y equals x squared divided by x, which is x. Okay, and then we're going to recognize the p of x and then figure out our integrating factor. So in this case, the p of x is this one. And we can also recognize our q of x, which is the thing on the right side. Okay. So let's find that z function integrating factor. Z is going to be equal to e raised to this power, p of x dx, which is going to be that negative 2x dx. And then by the formula, this is going to be e negative 2 1 over x dx, which is e negative 2 ln absolute value of x. And then because of the rule of the logarithmic function, we can put that negative 2 to the exponent of the argument, which is ln x negative 2. Okay, and then we can convert that into 1 over absolute value of x squared. And because the square will put anything negative to positive, so the absolute value is actually not needed. So we can write it as ln 1 over x squared. And we also know that the exponential function e can sort of cancel with the ln. So after it cancel, we are going to be left with 1 over x squared, which is our integrating factor. From our previous discussion, we know that we should multiply both sides by such a function z, which is the integrating factor. So let's do it here. We're going to have this multiply to each of the terms, and then we're going to have the first term being y prime 1 over x squared, and then the second term is going to become, let me put plus sign here, that's y, and then that's negative 2 divided by x3, and then right hand side being 1 over x. Okay, and also from our previous discussion, we know that the left hand side is going to look like the derivative of a product, which can be turned into that derivative of the product by using the rule. So if we take a look at the expression here, we see that this is y prime times this function and plus y function itself times the derivative of this function. So it's the same kind of product rule of the derivative. So we can turn that into y times 1 over x product derivative by the product rule, which equal to 1 over x. Next thing, just follow the procedure as before. We take the antiderivative on both sides with respect to x, which is going to help us remove this prime. So that's going to become this equal to antiderivative of that dx. And then we're going to proceed through, going to have this going to become ln absolute value of x plus c. Okay, the very last step is just to multiply both sides by x squared to get rid of that, so we can have y solved explicitly. So we will have y equal to x squared times ln x plus c, and then we should indicate that c is an arbitrary constant real number. So that is how we solve this question. Now let's summarize the steps, general steps of solving such a type of question. Summary. The first step to solve it is to put the equation in the standard form, which is y prime plus y times p of x equals q of x, which we did in that example. And the second step is to recognize your p of x in that situation and calculate the integrating factor z equal to that thing. And find z equal to e raised to this. Okay. The very last step, you just multiply both sides of the equation by this integrating factor and proceed through. Okay, I hope this video is helpful for you. Feel free to comment below if you have any questions. I will see you guys in the next video.